using crossbreeding or back crossbreeding to transfer them into different varieties. And finally, we have a multiple biotic stress resistant cultivar. So in this, I would like to acknowledge a major role played by All India Coordinated Research Project on Rice, which every year identifies not only very strong or very, very high level of resistance with regard to the major pests and diseases. And we also have identified several multiple biotic stress tolerant donors also. And with regard to molecular mapping, if I would like to, since there are many students are here, I would like to spend a few minutes in this particular slide. Whenever you undertake molecular mapping, the first and foremost task is in terms of identifying a good source of resistance. Preferably it should be monogenic, and you need to identify a variety which is susceptible to that particular pest or disease. Then you develop a mapping population. The most commonly used mapping populations are F2, F3, advanced up to F5 or F6 generation, by which time they will become both, they will be heterogeneous, but all lines will be homozygous. Individual plants in a line will be homozygous. But there are alternative rules wherein we can develop backcross inbred lines or near isogenic lines. Once you have a mapping population, a stabilized mapping population is always good. When I say stabilized mapping population, I'm talking about generations like beyond F5, like F6 or F7. And when it is backcross derived line, it should be at least BC1 or BC2, F4 or F5 generation, wherein the trait will not segregate any further. So once we have a stable generation, we have to go for large-scale phenotyping, high-throughput phenotyping, wherein each and every plant should be, every line should be phenotyped at least for 2 continuous seasons. And once phenotyping is done, we have got a lot of options in terms of genotyping. And I would not like to go into what all the different markers or steps used there. But at present, the most preferred marker systems in rice for genotyping are SNP markers. Different platforms are available in rice. If anybody is interested, you can write to me. I'll explain you a detail about which are all the genotyping platforms available for genotyping in rice, particularly SNP markers. And then once you have a marker system used for analysis of this fixed mapping population, then you develop a linkage map using those markers. Even though those markers' physical positions will be known already, but still this is the first and foremost task which you have to do it. Then finally you have to go for QTL or gene identification and undertaking course mapping, and then with a subset of that particular mapping population, you can do intercrossing and then go for fine mapping. And even though it's not essential to identify the exact location of the gene and identifying what is the causative gene underlying that particular trait, it will be desirable. That's why most of the cases what I'll be going to describe as of talking about molecular mapping, we didn't just stop at coarse mapping or fine mapping. We went up to the gene level, not only in terms of fine mapping them, but also characterizing them at functional level through genomic, transgenic, and also transcriptomic approaches. And finally, when you have a closely linked marker, in the case of, even if you don't have a closely linked marker, you can always have 2 markers flanking the gene, which can be used together. And if you have a marker which is part of the gene, these markers are functional markers. An example was presented by Dr. T.R. Sharmaji for PA54 gene. And once you have a good marker which is very closely linked to the gene, or 2 markers which are flanking the gene, or marker which is part of the gene, which are called as functional markers, we can go for large-scale marker-assisted selection using various tools or techniques. And how we are going to develop different methodology to transfer the genes, I'll be discussing later. Now coming to some of the own success stories with regard to bacterial blight resistance, my team together with Dr. Gaurishakar Laha and with the help of my pathology team, they have done very good work in terms of identifying. This is one of the genes which has been used as a flagship gene in many of the resistance breeding program. It's a gene called XA33. It was course mapped using SSR markers on chromosome 7 of rice. But recently, one of my PhD students, he has done the fine mapping, and we have identified the underlying candidate gene also. But Since we were dependent on low throughput markers like SSRs, ISSRs, and then RFLPs in initial stages, the progress was very, very long. It took almost 6 years for us to undertake molecular mapping, gene identification, and then gene characterization. But the scenario with regard to this has changed with the advent of genomic tools, which are very well described by Dr. T.R. Sharma ji. So now that we have got very good SNP markers and also high throughput genomic tools for candidate gene characterization, once my student, PhD student Pragya, she identified that one of the lines provided by IRI, an Oryza officinalis introgression line, it has got strong level of resistance against bacterial blight. She went ahead and did genotyping with 7K rice SNP markers available. And she was able to identify a major locus on chromosome 11 long arm, which is about 3 kb away from exate 21. And she has also worked to identify the candidate gene also. We were lucky because the underlying SNP was part of the gene. And we were then able to, through sequencing and also through transcriptomics, and then later through transgenesis and gene silencing, we were able to identify that the candidate gene is a gene encoding NBRC domain containing protein. This is another success story wherein my colleague Dr. Seshu Madhav, together with Dr. Srinivas Prasad sir's team, they have worked towards identification of major neck blast resistant gene. It also confers resistance to leaf blast also. This was identified from a wild species called as Oryza glumipetala. The introgression lines were developed by PAU, Ludhiana. So he worked initially with SSR markers and later with the high throughput tools like SNP markers, genotyping by sequencing, and other advanced tools which are available. He was able to identify the candidate gene, and this gene has been licensed to at least 3 or 4 companies for deployment in their breeding programs. And this is the power of mapping. So right from a day in which mapping population was developed, within about 1.5 years, we can easily undertake or identify the candidate gene and validate it also. And this is one recent example. I mentioned that sheet blight and false smut are gray areas, and they are not having very strong level of resistance. Of course, there are a few genotypes like TETUP and all, but the level of resistance is towards the moderate resistance side. So we have identified a northeastern landrace by my colleague Dr. Vijaypal Badana, who earlier worked at Nagaland, Manipur and all. So he brought this particular line. We developed a mapping population by crossing it with improved Samba Masuri. So we had a set of 430 RILs. So using that with SNP markers, with the help of NAPGR, Dr. Gopalji Jha's group, we were able to do a fine mapping using SNP markers. And we were also able to identify diagnostic SNPs, and we are now identified 3 putative candidate genes. We are now working towards that validation. And this work, I would say, that will get completed within a time period of 1 year. This is the power of genomics. This is the power of deploying advanced tools in molecular mapping. Then this is another typical case wherein my colleague Dr. Jyoti Badri, she works on population improvement with regard to sheet blight. So from a northeastern landrace called Fogak, which shows strong level of tolerance to sheet blight, she has identified a major locus called QSBR 3.1 on chromosome 3, and she is working towards identification of the candidate gene. And we have been successful to some extent because 2 genes show hyperexpression after inoculation with the pathogen. And similar is the story with regard to another gene conferring tolerance to BPH called BPH33. The original donor is from landrace called Velutachira. From that breeding line called RP2068 was earlier developed. We identified that this particular line shows strong level of resistance against BPH. So we developed a mapping population. This program was led by Dr. Bentur. So together with his team, my team has initially done the course mapping, then fine mapping with SNP markers, and we have identified that the candidate gene controlling this particular, responsible for this particular trait is a heat shock protein. And now we have developed candidate gene specific markers, and we are in final stage of varietal development with this particular new gene. And one important power of like say, we have been talking about biparental cross-derived mapping populations. Other popular methodology is called as association mapping, wherein historical populations or crossbred developed populations, larger in size, around 100 or thousands. Generally, they are used for trait mapping, phenotyping, and then validation. Through association mapping, my colleagues Dr. Kalyani and Dr. Somashekar, they have indeed identified some major loci located on chromosome 1, 2, 4, and 8 associated with rice root knot nematode, which is becoming a serious problem, particularly in upland rice and also direct seeded rice. This was done using our ICRIP network, wherein we have started a coordinated testing program even for nematodes also. With the support of our cooperators, we were able to achieve this. And right now, we are working towards that major locus located on chromosome 4, short arm. And we are working towards identification of the candidate gene with a biparental cross-derived mapping population with 2 donors. Then this another, I would say, a success of coordinated research. In coordinated research, under the guidance of Dr. T.R. Sharma ji, starting with the year 2023, we have been fingerprinting each and every entry nominated for our ICRIP trials, be it IHRT or IVT or AVT1, AVT2. Every year, we fingerprint around 1,200 to 1,500 entries using 1K RICE SNP platform. It has got representation of around 1,084 SNP markers. One lucky thing what we got out of it is I requested Padma Kumari madam to analyze the data with regard to stem borer tolerance, because we have a stem borer screening nursery carried out every year wherein all these 1,300 lines are subjected for this thing. Then she carefully selected some certain individuals and then developed a mapping population which doesn't represent a structure. And my colleague Dr. Kalyani, who is a genomics expert, could do an association mapping using this 1K RICA. And we were surprised to find very good associations, particularly on chromosome 5, wherein we got one single marker which has got a large peak. And as far as biparental cross-derived populations are very powerful in terms of trait detection and characterization, I would say that future lies also in association mapping. And we are going to use our All India Coordinated Research Project on rice data significantly for association mapping. And I would like to stop here with regard to, I've only given you a glimpse of molecular mapping because of paucity of time. If any student or anybody is interested, you can always write to me, and I'll be happy to assist you in various stages in which you require some help. Now let's talk about what are markers or what are major genes for which molecular markers are available, how they can be translated by developing better resistant varieties or hybrids. So in this regard, there are several breeding strategies. One breeding strategy which has been very, very popularly deployed for resistance gene breeding is backcross breeding, wherein generally in the background of a very elite variety, which not only has got a higher yield, but also a good grain and cooking quality, we try to transfer a few genes, maybe 3, 4, or 5. They may be encoding a single trait, or they could be encoding multiple traits. So backcross breeding or marker-resisted gene pyramiding is one of the most popular strategy. But of late, additional tools like genome-wide association study, wherein you don't look at single genes, which are either major or minor QTLs. So there are certain traits like, for example, sheet blight. We identified that even though there are some major QTLs are there, but even in Vazopec and Fogak, they are controlled by several minor loci also. So genome-wide association study will help you to identify the minor QTLs and then help us to transfer those QTLs into the background of our varieties. Then we have genome editing. I'll talk only about one successful example wherein genome editing has been deployed for resistant gene breeding. And I'll also briefly be touching populations like magic. And also, we also need to understand that conventional breeding is still used for resistant breeding deployment, but there are various challenges, and that's why molecular breeding is the right way for us to go ahead forward. As far as bacterial leaf blight resistance is concerned, based on our intensive analysis of our ICRIP data, wherein we have got extensive phenotyping information about various NALs containing different genes. For bacterial blight resistance, it is my understanding that a 2-gene or 3-gene combination from the genes listed here, XA13, XA5, XA21, XA33, XA38, and XA48 should give durable resistance. With regard to BLAST, already Dr. T.R. Sharma has very nicely illustrated. Gene combination like PA1 plus PA2, PA2 plus PA54, PA9 plus PA54, PA68 plus PA54, all the, in whichever combination PA54 is there, it gives good level of resistance. This I can say with confidence because based on our fingerprinting data of all our eCRIP entries, more than 90% of lines which have been identified to show good level of blast resistance have got the resistant allele of PA54. And with regard to brown plant hopper, even though we have got a few genes which have been identified to work very well in the country, but we don't have very good markers for them. We have got only SSRs which you can deploy. So we are deploying as a start BPH33 in our breeding program. And similarly for galmage, we have got genes like GM3, GM4 and GM8, of which we are deploying the two dominant genes, GM4 and GM8 in pyramid conditions. And we now have some success also with regard to breeding for galmage resistance. And in all these things, our target is variety which is resilient not only to a pest or disease, but also to multiple stresses. That's our end target of this particular program. Now, let me narrate a few important things about how we developed an improved version of Samba Masuri, which has got durable bacterial blight resistance. And even as on today, the area under this variety is more than 9 lakh hectares. And there are farmers who have been growing this at least for the last almost 12 or 13 generations. And if you look into why this program started, this was a time when I joined IARR. There are a group of farmers who are from Rayalaseema area, that is Nandyal area, and also from East Godavari. They grow Samba Masuri regularly. And they expressed, in 1998 it happened when I joined IARR, they expressed to my head of department, Dr. N.P. Sarmaji, that we are facing severe problem of a disease called bacterial blight. Then, in collaboration with Dr. Ramesh Sonti's group, who have been a pioneer in this particular regard, we together drafted a NATP project of ICR, and then we worked to deploy backcross breeding for development of an improved version of Samba Masuri. And in this, our target was that we want to develop a version of Samba Masuri which looks like Samba Masuri, which yields like Samba Masuri, and which cooks like Samba Masuri. And it should also have the resistance. We should not lose anything from the background with regard to Samba Masuri. So at that point of time, we were not very sure how many backcross generations we had to grow. We went up to BC4 generation, and we deployed markers not only for selection of the target genes called as foreground selection markers. We also deployed a set of SSRs which could distinguish between Samba Masuri and the donor parent. 2 minutes. And Samba Masuri with regard to the presence or absence of the genes. Through this effort, we could develop one of the first products. Of course, there is another product parallelly developed called Improved Pusa Basmati 1. Improved Samba Masuri has got 3 major resistant genes, XAF 21, 5, and 13. And this is a success story of not only of deploying the right kind of rice science for improvement, but also about interinstitutional collaboration. Our collaboration with CCMV is continuing for the last almost 25 years or 28 years. And this variety is doing really well. And what is important for you to understand is that under field conditions, it is even as on today, it is standing very, very tall in terms of resistance. As you can see here, on the right side, you have got panel which has got improved Samba Masuri. It is totally free from the disease. Already grain maturity has started. On the left side, Samba Masuri is there, wherein it's severely affected by bacterial blight disease. And this has already been described by my colleague, Dr. Srinivas Prasad, wherein the background of improved Samba Masuri, another gene called XA38 was added. And this also Dr. Srinivas Prasad has already narrated. And another interesting development is a recent release called as DRR 85, which combines bacterial blight resistance with galmage resistance. It showed immune level of reaction in several galmage hotspots along with bacterial blight resistance. And we have added a trait of salinity tolerance in the background of improved Samba Masuri and developed DRR 58. Then another important development is adding low soil phosphorus tolerance, which can reduce phosphorus fertilizers. It is doing really well in Gangavati area of Karnataka. And finally, one important version is development of bacterial blight blast and then submergence tolerance version. This was recently released, wherein Dr. Fiaz has taken a lead role in this development along with Dr. Prasad. And we also have a success story wherein we transferred QTLs associated with high zinc and developed a version of improved Samba Masuri called DRR 48. And finally, this is a flagship product in which it has got multiple traits. It has got bacterial blight resistance controlled by 21, 13, and 5, blast resistance controlled by PA54, and it also has got yield enhancing genes, SCM2 and then OSSPL14. This is a collaborative work wherein we got the donor lines from IRRI, and this variety is doing really well. In fact, this Kharif season, we had a Dharwad Bay farmers who wanted more quantity of seeds of this variety, and it's spreading like a wildfire in Samba Masuri growing areas. And this is what I would like to tell, that through proper planning and through proper deployment, we could add value to Samba Masuri by initially developing bacterial blight resistant versions, then blast resistant versions, then BPH resistant versions, garbage resistant versions, and versions which have got tolerance to abiotic stresses, and finally, versions of Samba Masuri which can give higher yield also, and with better nutritional profile. And we could do the same work in Swarna's background also, wherein along with bacterial blight and blast resistance, we could transfer some of the yield enhancing genes also. And I would like to talk about just I'll take half a minute, sir, in this. Some new tools are available with regard to accelerating breeding for durable biotic stress resistance. The first and foremost tool is gene editing, wherein a collaborative group led by IRRI, along with Heinrich Heinz University in Germany, they have edited at least 3 or 4 loci. These are genes called as susceptibility genes, like XA7, XA13, and other XA genes, which are known to be recessive-resistant genes. So the promoter part of these genes are binding sites for transcription activators called TAL effectors. They could edit the promoter part of these genes, and now we have got durable resistance against multiple strains of this particular disease. But these developments are parallelly going on in India, identifying different targets. But this is one example wherein we are expecting the lines to be received in India, and then we'll be testing against different strains in the country. And another important tool is called as haplotype-based breeding. You all may be knowing that haplotype is a group of DNA markers which are closely linked or co-inherited. And we have got several favorable haplotypes and then several non-favorable or unfavorable haplotypes for several traits. For example, for yield, these are all the different genes and their favorable haplotypes. Deploying this approach, my colleague Dr. Jyoti has developed a very good variety called DRR-Dan 87 in the background of a variety called Swarna. And this particular breeding approach, we followed a recombination breeding approach with a reduced backcross breeding approach. And this version has got tolerance or resistance against multiple pests and diseases. And of course, speed breeding is something which can really accelerate our efforts in terms of rapidly developing multiple biotic stress resistant varieties as compared to just 1 or 2 seasons in a year. With collaboration with IRRI, we have demonstrated that up to 6 seasons can be taken up. And even in wild rice also, it can accelerate the breeding process. And finally, one important component I would like to touch upon is artificial intelligence. If gainfully deployed, it can be used in terms of predictive risk modeling, AI-powered phenotyping, and it can accelerate the process of genomic selection or genomic prediction. And even in gene discovery also, it has got its own use. And speed breeding can be accelerated through the application of AI tools. And if anybody is interested, I was deeply impressed by reading this paper by Farooq et al. It gives a very good workflow regarding how we can deploy artificial intelligence in breeding process. And finally, just in a slide or two, I'd like to tell what did I gather in the last several years of my work at IRR. So if you look into it, breeding climate resilient varieties through genomics-assisted breeding should be our target. Towards this, we clearly demonstrated that interinstitutional collaboration, not only between IRR and CCMB, IRR and several other institutes, whatever I presented is because of collaboration, not only within the institutes between different disciplines, but also with other institutes. So I would like to mention here that interinstitutional collaboration is the key for success. And another important point is that molecular breeding is already started delivering products. Already about 2 million or 2.5 million hectares is under molecular breeding derived products in the country, in rice particularly. And another take-home point is that it should not target improving only 1 or 2 traits. You should always be ambitious or over-ambitious, and multi-trait packaging through genomics-assisted breeding is a way for us to forward. We have demonstrated in the background of Swarna and Samba Masuri, and CRRA has done it in several backgrounds. IRA has done it with the help of NAPB in terms of adding value to several Basmati varieties. And finally, what I would like to mention here is that genomics should be increasingly deployed, not only for gene discovery, but also for accelerated gene deployment. And what is important for our, as a country, is that there are several novel sources of resistance. We should work towards identifying the functional basis of resistance or tolerance, and we should work more in this direction, just like the way Dr. T.R. Sharma's group has worked. And of course, the new tools which I described, they can certainly complement the process of breeding. But finally, I would like to mention here is that we started our work like a bullock cart. We were using RAPDs, ISSRs for breeding for biotic stress resistance. When I joined, I started a program for marker-stud breeding, and we were using a few markers like SSRs, ISSRs, CAPs, and all. And now, my team is traveling in an SUV, wherein we are deploying high-throughput genomic tools, not only for gene identification, but also for gene deployment. Finally, this is my concluding slide. A breeder can ask a question, whether can he use biotechnological tools for improvement of a trait? The answer is definitely yes, but we need to remember that biotechnology is one among the several tools available for a breeder. At the end of the day, biotechnological tools like MAS, molecular breeding, genomics, can only complement and then supplement the process of breeding. It will never replace the process of breeding. And we should embrace all these modern tools in day-to-day breeding. With this, I would like to thank all my colleagues who worked with me. Some of them are here also, and also my funding agencies who have been very, very extraordinarily generous in terms of funding all these efforts. Thank you, one and all. Thank you, sir.
Thank you very much, Dr. Sundaram. Very nicely presented how we can map new genes for different traits like BLAST, BLB, and also insect resistance, and then how to deploy. Actually, I think major impetus on molecular breeding was started from Indian Institute of Rice Research, where you are heading now. And almost all varieties which we are cultivating in India are marker-assisted derived varieties in rice. So that is all because of the leadership which you are providing there to this whole rice improvement program in the country. Since we left with very less time, but still we can have one question. So it's difficult to choose between Dr. Tikku and yourself. You can decide yourself. Okay. चलो आप पूछ लो पहले.
What are happening with the molecular breeding all?
Sir, I couldn't hear you, sir. Can you keep the mic closer?
Hello. Okay. We have seen in majority of the crops, including rice, that the developments what are happening with the molecular breeding are with respect to the stable varieties. For that matter, Samba Masuri, which is a well-known variety from the almost all years. Now you suggest me, your opinion I want to know, whether we need to start a fresh breeding with like magic populations involving all these genes, or we have to go with a stable variety, means ABT advanced varieties should be taken, my opinion. ABT advanced varieties should be taken into this molecular tool interrogation program.
That's one way to look at it. We always, when we started our molecular breeding program, we look at low-hanging fruits. And one easy strategy is marker-assisted backcross breeding. But believe me, in forward breeding, if we deploy the right set of markers, the right set of traits, it can transform breeding. One typical example is DRR 75. It was not developed through backcross breeding. There was only one backcross with some improved Samba Masuri, and further it involved crossing with several parents. But we have been successful because we had a large population size. We were able to identify a plant which was similar in grain quality to Samba Masuri, and we could transfer at least 4 or 5 different traits. And another example is DRR 79, wherein at least 7 or 8 traits have been added in the background. And that was both DRR 75 and DRR 79. They were not released through NAL trials. They were released through ordinary trials, wherein the lines had to be tested against the best variety and tested for 3 years. So I think while there could be a case wherein good variety, we need to make it great by adding a few traits. I think we should invest more on approaches like marker-rested forward breeding and then recurrent selection and magic population, and invest less on marker-rested backcross breeding, sir. That's the hard lesson I have learned.
Okay, from student, any question?
Yes, go ahead, sir.
So, okay.
Sir, good afternoon, sir.
Achha, yeah,
Myself, Harish, PhD scholar, sir. Sir, in GWAS, we are identifying SNPs for particular traits, sir. So now there is pan-genome approaches are available, sir, where whole set of genes are identifying and we can do large integration, sir. So can we use some phenotype and genotype matrix of pan-genomes for GWAS analysis as an input?
You have raised the right point. Initially, our approach in GWAS was only using the primary gene pool, that is the varieties and land races. But of late, the thinking process has moved differently. And we have started deploying even some of the wild relatives and other exotic genomes also. But you need to understand that genome-wide selection or genomic selection is a work in progress, because we have just started with our ICRIP trial data, both phenotype and genotype data. Every year around, we have got the phenotype data for at least 12 or 13 different traits every year. But it's a work in progress, and we should certainly move from the primary gene pool to a pan-genomic approach. You are right in that. But progress will come in, say, another 3 or 4 years or 5 years, when we'll have a large set of products developed through genomic selection. Thank you. Thank you. Thank you.
Thank you, Dr. Sundar, for a nice presentation. Now I would like to invite Dr. Amresh Chandel, rice breeder at Well Monsanto, Hyderabad.
Respected Chair, Co-Chair, honorable dignitaries, and all the delegates present here, thank you for this invitation. And we are all very proud of the fact that India has achieved #1 status in rice production. And all my fellow colleagues, scientists, distinguished scientists who spoke before me, have a very big role in that. And also all of you have very big role who have contributed to this success. But this conference on multiple disease resistance is a very apt moment where we know that we have a lot of potential in rice and how we can go forward together as a private sector and public sector. So good afternoon. My name is Amresh Chandel, and I work in Bayer Crop Science. I will be presenting a private sector overview of how we can work together and what are the new approaches we can take in achieving the success for rice production in India and also in Southeast Asia. So my presentation is overview here, context, then modern molecular tools, gene pyramiding strategies and regional evidence, CRISPR advances on multi-stress regulation, digital phenomics, economic and sustainability impact for farmers, and also buyers' rice journey and future outlook, then the conclusion. I know the time is running late. I will try to finish fast because we have some interesting oral presentations also. Now, what are the field realities driving the modern rice breeding? These are the key challenges we see in the field. Insect pests, we all know. Viral diseases, which are becoming very important now. Multiple pathogen pressures and rapid biotype shifts are happening. In the conventional breeding, we do have constraints like difficult to stack multiple resistant genes without introducing linkage. Long breeding cycles delay delivery of improved varieties. Phenotyping multiple stresses simultaneously is inconsistent and labor-intensive. Limited ability to track complex gene interactions using traditional tools. Now, why precision, speed, and data integration matter? because we need to combine many resistant traits cleanly and efficiently. Faster selection cycles enable quicker deployment of resilient products. Data-driven phenomics and genomics improve accuracy, confidence, and decision-making. And integrating molecular tools with digital analytics accelerates genetic gain under multi-stress environments. What are our advanced tools and platforms for rice resistance breeding? We do have molecular tools like marker-assisted selection, which all of you are very much aware. Then we have gene silencing, RNAi approach, and genome editing, CRISPR-Cas, which is a new upcoming technology. On the advanced platforms, we have speed breeding, which is changing the way we are getting genetic advance faster. Then double haploidy, another approach. And genomic-enabled trait discovery. This is how integrated pipeline looks like for multi-pest and disease resistance in rice. First is a discovery phase, then we do markers and edits, then the stack the design, rapid cycling using speed breeding, phenomics, and it goes to the field testing. Then predictive analytics are applied, and finally deployment and impact happen. This all can be done within a span of 5 years now, but previously it took 12 to 15 years. So this is how we have to integrate our multiple disease resistance in rice. And on the genome editing strategies for disease, this is the way it goes: as gene knockout, optimize the alleles, promoter and cis editing, multi-target stacks, and again validation and deployment in the markets where you want to release the product. On gene pyramiding, context and rationale in South and Southeast Asia. Why do we need gene pyramiding? Because we have major regional threats like bacterial leaf blight. It is very diverse, evolving races across India, Bangladesh, Vietnam, Philippines. Rice blast, again, a multiple magnoporthe races are there. BPH has different biotypes, and emerging bacterial leaf streak. BLS is becoming very important, especially in Southeast Asia. Our production goal is to enhance durable, broad spectrum resistance without compromising the yield or grain quality. What are the breeding strategies which we employ? First is a marker-assisted pyramiding, which remains the most effective and scalable approach. There have been recent evidence where IRI, Bangladesh Rice Research Institute, and many Indian programs have effectively utilized it and released the products. Optimal pyramids include 3 to 5 resistant genes or QTLs to avoid linkage drag or yield penalty, and increasing use of newer R genes like XA23, 47, 50 in the elite backgrounds. And what is the target profile we are looking at? A high yield product under Swarna or MTU 1010 mega varieties background, suited to irrigated and rain-fed lowlands, and strong tolerance across multiple pathotypes, which is very evident from the ICRIP trials where both public and private partners give the products for testing, and we are seeing a very good products coming out of that. Gene pyramiding recommendations from my side here, based on evidence. The first recommendation is, I'm sure many of you might be following this, but this is just to reiterate that broad BLB plus blast resistance is the most validated, where XA5, 13, 21, and PI54, PI9, these combinations are proven durability, where many products have been released. The second can be on XA23, 21, 5, and PI54, or XA47, 21, and PI9 for the enhanced durability. Then the third is a multi-pest, where BLB, BPH, and blast, all three can be combined in one product. And the fourth will be advanced next generation options where we can use CRISPR strategies also. What are the practical deployment and expected outcomes? On the breeding methods, marker-assisted selection takes 2 to 4 years for introgression, where you use tight markers for major genes and validate with background recovery phenotypic screening, which you all very well aware. Outcome is 20 to 40% lower disease severity, maintained or improved yields, and stronger resilience against the evolving races. So this will help us in regenerative and climate-smart rice systems. Recommended target backgrounds are again the mega varieties, MTU 1010, IR64, Siherang, PSB series, and partners and pipelines. So we have to work together. As Dr. Sundaram told that there is a very good linkage between partnership between national programs and state programs. I would add a private partner also there. So come up with the projects where public-private partnerships can also work together in a NARS program, which will help to fasten the process. On the CRISPR, let's see what are the rapid progress and why the CRISPR matters. Because this is a precise targeted edits with no foreign DNA. Faster breeding cycles, minimal yield penalty, and ideal for South Asia and Southeast Asia. Which key traits are improved? Yield and plant architecture, higher yield, unchanged quality, D3 knockouts give 22 to 38% BLB lesion reduction, and also OS, APL, GLW7, GLW7 edits improve the grain size, nutrient flow. Grain quality and nutrition is also improved. For the BLB blast and multi-stress resistance also, CRISPR has been utilized. These are the major breakthroughs where broad spectrum BLB resistance effective against diverse Asian and African strains was demonstrated in IR64, Siherang, Sub1, and other mega varieties, and there was no major agronomical penalties. Additional disease resistance targets where this B9 mutation can enhance BLB resistance, D3 edits, and both BLB to enhance architecture benefits and multi-disease packages. For abiotic stress also, drought, UV tolerance, arsenic reduction, and other enhancements like herbicide resistance and grain appearance can be done using this technology. What is the regulatory status and application in South Asia? India is the fastest deployment. You all know, last year we released Pusa rice DST1, DRR Dhan 100, Kamala. These are the 2 gene-edited varieties. On the regulatory part, SDN1 and SDN2 edits exempt from GMO rules under India EPA Rules 7-1 and expanded field trials after 2024 regulatory relaxation and high relevance to India, BLB, drought and salinity. In Southeast Asia, there is an ongoing ERI and national collaborations, testing of CRISPR suite edited BLB resistant lines in IR64 background, and commercial approvals are slow, but edits without transgene may be non-GMO depending on the national policy. Then integration with the traditional breeding, where CRISPR suite promoters are edits or complementary pyramids like XA23, 21, PI54. This enables durable resistance without relying only on the resistant genes. These are the challenges. Off-target editing reduced in newer tools. So this is reduced now. Public acceptance and IP constant. This is one of the biggest challenge. And harmonization of the regulatory framework. But we all are working together to overcome these challenges. I am sure within few years it will be overcome. These are some of the reports of pyramiding BLB, blast, and BPH in elite backgrounds. On the left side, you see marker-assisted breeding from the India. Popular cultivar Tela Hamsa was improved by pyramiding these XA21 and XA13 gene. And also in Tamil Nadu, TNAU, stacking of different genes was done in ASD16 and ADT43. Similarly, in China and from Bangladesh, there are some reports. These are very latest development. And multi-local validation, evidence from the trials. Tela Hamsa pyramided lines validated at 3 blast hotspots and 2 BLB locations. They exhibited high resistance across environments, supporting the spray reduction potential. Similarly, BRRI Dhan 63 pyramided lines, they achieved near immune scores 0 to 1 across test, and multiple lines demonstrated higher yield than the elite check, implying fewer fungicide and bactericide applications for equivalent production. Again, for ASD16 and ADT43 with blast, BLB, and sheath blight resistance. Farmer impact, yield and resilience. So here we see several lines in BRRI Dhan 63 having more than 28 to 30 gram per hill and near immune disease scores. This reduced input cost and lower the crop loss risk. And stacked packages in the elite background, both in China and India, they maintain agronomic traits, broaden the resistance spectra under the biotype shift. And again, this is a public-private workflows where we can combine resources and work together. Genomic resources for BPH. Digital phenotyping and data-driven breeding decisions are now being taken across in private sector and public sector, where digital phenotyping and data-driven breeding decisions are very important. And then it combines analytics and gives us a digital dashboard where we can take decisions faster. What are the sustainability benefits of resistant rice varieties? Outcomes. First is a fewer pesticide application, lower pesticide residues, improved safety of ecosystem, enhanced resilience of climate variability. And for the farmer, what is the value? Cost saving from reduced spray, higher and more stable yields, reduced production risk, and better access to the premium markets. The Bayer has a rich history of bringing disease-resistant products in the market. Bayer is the first company one of the first company which released the BLB-resistant hybrid, BLB and BPH-resistant hybrid back in 2008 with the name Arise Dhani DT. This is the hybrid for the late maturity market, and it provides protection against both BLB and BPH. Later on, Arise 6444, which is one of the best-selling hybrid till date, was also introgressed with BLB and blast genes, and it is available in the market. And over the years, you can see we have been bringing products which are climate resilient and having both biotic and abiotic stress tolerance across multiple segments and markets. Today, at Bayer, we are giving products for all the segments, all the market segments present in India and Southeast Asia, and with these resistant genes. Arise 8433DT, 8455DT, 7006, all these products are there. This is the Arise portfolio where climate resilient performance across diverse and variable environments, abiotic stress tolerance including drought, submergence, and lodging, biotic resistance package against major pest and disease like BPH, blast, and BLB. These are some of the pictures which validate our products. In the middle, you can see Arise Dhani on the right side gave 8.3 tons per hectare. And on the left side, the other cultivar gave only 1.7 tons per hectare under the infestation. This is a farmer field photograph, real time. Similarly, you can see other photo where Arise Honey DT, Arise 6444 Gold crop is standing very well, but other cultivar which are not having resistance gene are affected by the disease and pest. Now, what is the economic contributions of disease-resistant rice hybrids to the regional system? Here, we can see over the past 10 years, Arise products have given a better return to the farmers compared to the other cultivars when grown in disease-prone geographies. And this is the economic value of the disease resistance in rice, which impact across the yield levels, where we see in 3 to 16% yield loss. Still, if you grow resistant products, farmers can get better returns. These are the conclusions now. The first is integrated molecular tools make multi-stress resistance practical. Digital phenomics accelerate accurate selection. And collaboration is the key to scale. Thank you for your attention. My contact details are here. If any questions, you can send it across. Yeah. Thank you.
Thank you, Dr. Chandel, for excellent presentation. And you have covered various aspects on rice, what we should do in India and globally, and what are the options available with us, and giving little bit information about your company's work. That's too in a very confidential manner. I was discussing with Dr. Saab that what are the genes which you have deployed in various cultivars, probably you don't disclose. So anyway, it's your policy, but I think students or anybody can ask question. Dr. Saab, Dr. Krishnan Kumar.
I was listening to all the presentations on rice. We have a tremendous post-harvest loss after rice is harvested. And most of the time, our products or our rice exports, whether it is in broken rice or it is in the other formats, often get, I think some effort now slowly should start with respect to the breeding those genotypes which can also confer post-harvest resistance in whatever is because we almost take it to the grain, and it's a very sad story to see that if our product is rejected both within and outside. I don't think, in my view, that kind of an approach has been very intensely done. But since you said it's a institutional collaboration, I see that Bayer, if they can join hands with others and also see if we can take it forward, it will be very, very great advantage to our country, since we are also one of the largest producers and exporters.
Thank you, sir. Thank you very much for your comments.
Yeah, thank you, sir. This is very well commented, and this is need of the hour. But I would also like to say that if we harvest the grain at right moisture, we can still reduce all these post-harvest losses. But we have to work together on these technologies. Yeah. Thank you.
Okay, thank you. Any other question? Okay, Dr. Chandel, there is no question. Thank you very much for your excellent presentation. So now we have 3 oral presentations, and each presentation will be for 10 minutes. I will request my co-chair, Dr. Gowda, to kindly invite all the presenters, and we can listen to them. Dr. Gowda.
Yeah, thank you, sir. Now, first, I would like to invite Ashita Joy.